we can see, and I think it's part of it because the technology is just getting better, right? And more AI developers and products are available in the market. But I think most importantly, the government itself has caught up and provide more guidance, more way to how to safeguard and promote the use of the AI. If you follow, early this year in March, the the EU Parliament adopted the EU AI Act in the European Union, after many years of negotiation among the member states. The EU AI Act is the first law on AI in the world. So it really paved the way to the approach to AI that created something that's ethical, safe, and trustworthy. So this is going to be important for us to keep track on. Next slide, please. So in the US, executive order on AI that was issued last October, I think that's a tipping point in the US. Before that, AI conversation focus on risks and harms and how to mitigate those risks. As you can see here, it's several years ago, OSTP, the Office of Science, Technology, and Policy in the White House, issued a blueprint for the AI Bill of Rights. And early last year, the NIST issued the AI risk management framework, which is great, in terms of looking at how to mitigate the risk of AI in the U.S. So since the executive order last October, more and more, government agency have been take the leadership on the AI and to come up with the guidance and and way to how we not just mitigate the risk, but also how we promote the benefit of AI. In Congress, we start seeing since last fall a bill, the bipartisan bill in the Senate that tried to codify the NIST framework of AI. And also early this year on the House side, the bipartisan task force on AI was established. So this is something that we are tracking and then see how the AI regulations and or potential law in the US is going to be a long road, but at least in the government we start seeing the product and policy. Next slide. So this is happening in March this year early. This is followed the executive order back in October that I mentioned. The OMB, the Office of Management and Budget in the White House, issued the AI policy. This is a little bit more detailed policy following the executive order. It's the first US government-wide policy for the executive branch agency to come up with a way to mitigate risk and also the use and promote the benefit of AI. Right now we start seeing more and more like how we can use this new technology. And this is where, a lot of things hasn't spelled out more than before in terms of executive branch, federal government agency can do or should be aware of in terms of AI. There's some requirements that this agency has to provide the use cases that they use AI for their own programs and projects so that, government have a single location to be able to keep track on use cases. In terms of workforce and governance, it has expansion of that, and we can start seeing, the federal government hire more and more AI professionals, and GSA has, got some funding this coming year, or even expand on existing training program to kind of help federal government agency to be educated and have more knowledge on the AI. So each agency is supposed to have the chief AI officers and all the government board that govern the use of AI. So it's something we've been keep track in on this AI policy and also the technology that we're going to talk about later. So I'll end it with last year. The way I see it, we may be skeptical, about AI. I think that this year and this coming year, I think AI is going to be more and more important, and it's going to be with us before we know it. And I think we should be at the forefront of this technology and, working together to kind of see both risk and benefit, right? And I'm glad that we are having conversation today and looking forward to have more conversation at the conference and, particularly with the AI experts out there, and also, how we can work together to looking at both risk and also benefit of AI. Thank you. I'll pass to Jana to talk about the.
Okay, thanks, Pamano. Okay. Hello, everyone. My name is Yana Ma, and I am co-chairing this subcommittee with Pamano. So I'm going to give a quick overview of this group, and then later I'm going to introduce our speaker today. So this group, we're trying to make this group as a core group where we can share knowledge about this evolving AI technology and actively looking for best practices which can transform our current technical and policy solutions for floodplain management communication community. So the current structure, as shown in the slide here, we are on the top. We have ASFPM membership and communities, and then policy committees, and then under policy committee we have higher education committee. So AI subcommittee is currently under the higher education committee, as David mentioned at the beginning of this webinar. So at this moment, we're still in a very early planning stage. So we developed 4 objectives for this subcommittee. The first one is to bring AI awareness to this community, so people know this something is coming to us, and bring the awareness to everyone. The second goal is trying to gauge AI interests, so we can have a understand of the comfortable level of the community here about the new technology. The third point is about we want this venue to be a safe place. Everyone can start exchange knowledge, which not only limited to technology or policy discussion, also about AI ethics and about data privacy and data security topics, to making sure the trustworthy AI solution can be adopted in our domain correctly. The last bullet is about collaborations, because the technology itself is moving very fast. So I think besides the traditional public sector and private sector partnership, we also needed to invite people from academia, where those people actually sitting on the very front to look into those new technologies and how we can use those technology correctly. So how to get involved with us? If you have your phone ready, handy now, you can just quickly scan this QR code. This QR code is gonna direct you to that survey form, which we actually put the link in the webinar invitation. That's the same form. So basically we use this form to collecting some basic information of everyone, knowing your level of AI knowledge and knowing your interests directions. So we're gonna gather all the information and then plan the activities in the following future. So just take this QR code and fill in the form. Okay, so with that, I am happy to introduce our speaker today, Dr. Wang. He's an assistant professor in the Department of Civil and Environmental Engineering at Rutgers, the State University of New Jersey. He finished his PhD in MIT and also conducted postdoc research in both UC Berkeley and MIT. So his research focuses on resilience of coastal system and marine renewable energy. He employs emerging sensing and modeling techniques to investigate the effects of climate change and human activities on coastal areas. We put the link, his lab link, in this slide deck. So if you're interested, definitely check it out after the event. With that, I'm going to turn this over to Dr. Wang, and Dr. Wang, you can share your screen.
All right. Thank you, Yanan, for the introduction. Good afternoon, everyone. Can you hear me? Can you see my screen?
Yes, we're seeing the whole desktop, I think, if you want to switch to your presentation.
Okay. Does it work now?
Yeah, it's in the presentation mode, I think. No, it's actually in the slide. You probably needed to share the other screen.
Stop sharing. Does it work now?
Okay. Yes.
Okay, thank you very much for the introduction. And hi, everyone. I would like to thank you, the subcommittee, to invite me for this presentation. So today I would like to introduce some of our exploration to use AI for the application in floodplain management. My name is Roger. I'm from Rutgers University. For this talk, I think at the beginning, I would like to briefly introduce what's AI and how to use that, what's the general framework, what's the frontier that AI application so far. And I would like to use 3 stories then to introduce some of our studies. At last, I would like to also mention some other research directions, maybe not focused in our lab, but still very active in the research and the applications. As a starting point, I think I would like to point out that actually AI started very early, and it has a long history of being the next big thing. So you can see it's even in 1950s, people start talk about the AI. But as the other technologies, AI has the peak and also the winters, so like the valleys here. You can see AI Winter 1, AI Winter 2. I think the recent AI revolution coming after the 1997, the Deep Blue beats the chess championship, Garry Kasparov. And also later on, when people develop IBM's Watson, and then 2016, which is actually very big milestone, is that deep learning is for the first time beat the world's championship in the game Go. That's probably the most complex game that people have invented in history. So that's after that, the AI has been used for many fields. So here is well, different people have different definition for machine learning or AI. Here is the example that I captured from Penn State, UPenn's CIS class. So generally, it says before, when you have a bunch of data, if you want to process the data, you design a series of rules, and then you formulate that into a program, and use computer, you can process the data and get your output. This is traditional way of programming. But machine learning following different philosophy. Generally, it doesn't. People don't need to design definite rules at the beginning, but they use data and give some sample output to train a computer model. At the last, this computer model is capable to receive new data and process that into some output for people's use. So that's if you think about that, it's a different input-output way. What I would like to say is machine learning is more like a way you deal with input and output. For example, this is the basic function for any field. If you give input X through a function, it gave you Y. Traditionally, we can define the function as many different formats. It could be polynomial, it can be sine, cosine, can be exponential, it can be anything. So that it really depends on what's your basic knowledge and what's your expectation from the input output. So you can design this function to meet your requirement. To get this to obtain such a model in a traditional way, we need some optimization methods such as the least square or programming. And a lot of times people just use try and error, try to find out the coefficient here, like A, B, C, D, etc., such that they can try to obtain the best combination of these coefficients to achieve their goal. However, machine learning is following different philosophy, as I mentioned. If you think about that, people actually knows little about this, how machine learning works. Well, I would like to see more and more studies now focusing on how to interpret the black box here. But in general, if you give input, machine learning is can be seen as a black box. Given this input, it's so flexible, so powerful that it can give you whatever output you want. The idea is you give enough input output to tune this black box, and then in the future you just need to use this black box to make a prediction. So that completes the loop to make a prediction with this function, but this time the function is just a black box. Well, it's one of the most famous black boxes, neural network, and people still are trying to understand how it works. Here, I would like to mention, well, the design of this black box definitely is an art, and I think for application, we need to understand how to make the black box, how to test the black box, and where to use the black box. And I would like to, following these questions, to give a deeper insight into this machine learning and AI. So generally, there are two types of machine learning. One is called supervised learning, which means you give labeled data, and you also give the some label results, and then you train the machine learning model. The machine learning model, and in the future you use some test data to test whether the tuned machine learning model is good or not. And in the future, you can just make the prediction. There's supervised learning. We also have unsupervised learning, which means you don't need to give a labeled data. You just give a lot of input. And now there are very many algorithms that can be used to classify and find the patterns or cluster the different data into different groups. For example, now the popular method like a support vector machine and neural networks, these are very good unsupervised learning methods. Unsupervised learning method, people also develop other methods. This is what looks like in the black box. So, for example, it can be logistic regression, or it can be random forest. In another way, think about this machine learning is before we use the linear maybe a straight line to classify different data, but obviously it cannot be perfect. Well, people develop new methods. For example, they design some specific rule that you can better classify the data into different groups. So I think the next question is when we need machine learning, where we should use machine learning. And here are some guidelines from this University of Pennsylvania's class. So generally, first of all, if the data is a huge data, especially when it's called a big data, you have the 3 V's, big volume, big velocity, and big variety. So you have different types of data, very big volume of data, and the data is generated in a very fast speed. If that's the case, machine learning probably can do a good job, and the traditional method usually has a limitation to process the data. On the other hand, when the task requires the customization, for example, email filtering or personalized surveys, if that's the case, machine learning probably can do a good job because it can be customized easily. On the other hand, when humans' knowledge has a limitation, or we have a limited knowledge of, if sometimes just the data is too much uncertainty in the data, so we probably machine learning can also do a good job. For example, when we these tasks as humans we do every day, like a facial recognition, understand other speech, even for expertise judgment, for example, medical diagnosis, we usually had a difficulty to formulate these how people make decisions in these fields using humans' knowledge. Or in other fields, we even don't have the knowledge. For example, the space exploration, undersea manipulation, cellular robotics. When we don't have such experience in the before, how do we still finish our jobs? So for these tasks, people argue that problem machine learning has a good space to be used. Here's a classical example how to recognize the digits from handwritten numbers. So you can see from these from a real person's writing, you can see that how do you define which is number 2? It's quite tricky, right? And how do you do that? Well, people always can recognize, okay, maybe this is 2. You have some judgment, but how do you teach a computer to do that? That's the question. And machine learning, different from traditional programming, machine learning can relatively do a good job here. On the other hand, I think some other examples, for example, medical imaging, handwritten or spoken words, generating patterns, recognize the anomalies, and make predictions, especially when you need very fast predictions. I think machine learning has very good applications. So as a brief summary, I think I would like to say that machine learning is a way that we can build a model to predict things without knowing too much about how it works mechanically. You can just what you expect is what from input to output. You don't need to know what's in the middle. You just expect that this is what I give and this is what I expect to receive. And then that's how machine learning. Just a few more words about between machine learning and another hot topic called deep learning. I think the basic difference is machine learning before they use feature extraction to filter the data into this classification because the neural network before cannot take very many input, and deep learning in general combining the feature extraction and classification together. In this way, actually, at different layers, with many more layers, the model is more flexible, and people found that it's more accurate than machine learning before. If you look at the categories, people always say artificial intelligence. Actually, it can be more broad. Machine learning is just a subset of this general artificial intelligence method, and deep learning is an even smaller subset of machine learning. So you can see that that's how the relationship is. Okay. So I think that's the basics about AI and machine learning. Next, I would like to use some stories and how our lab is looking at this problem, what we can do. So in general, we are dealing with aging infrastructure problem and also climate change. As the boom of big data and machine learning, we can see that in many fields now, machine learning has been used. My question my research lab is working in the field and see whether there is opportunity that we can combine this to address the infrastructure, climate change, and more closely to our talk today is how we deal with flooding. So the first story, I think based on my experience, I think machine learning actually has a very good use in data mining, especially for some unstructured data. For example, today I would like to share some of our work on how to extract data from from social media. This is the numerical model that when I was doing a postdoc at UC Berkeley, you see that my advisor told me, hey, you should develop this hyper-resolution numerical model to simulate floods. I said, why should we do such high resolution? Well, it's one way that you can get closer to the residential So our idea is to develop a parcel resolution numerical model. In this way, we can better engage the stakeholders for this project. But I spent like 3 months trying to find the good data to validate the model. Developing this model is not that tricky. You can always find some commercial or open source software and using the topography and develop a numerical model. However, validating this model is a really big headache. I searched like a remote sensing sensor network, but these data are usually not available or not available for the target area you are looking for. Remote sensing usually has a very low frequency of scanning. Sometimes the resolution is too poor to be used. Sensor network is very expensive to install and maintain in the urban area. And if given such large area and high installation cost, usually the network just simply not available. I think the best data are still the witness survey. So what happened is the people like USGS or other government agencies, after flooding, they go to the community to collect the flooding information, which can be biased, inaccurate, and incomplete. Insurance reports is another data source I checked, but it's not very useful. Most companies just refuse to share those reports because it's a commercial secret. After doing that, I think what happened if I check social media? At that time, social media is really booming in 2017, 2018. So this is a typical tweet, very informative tweet about flooding. For example, this guy shared where the flooding was happening and how deep the water was and what's the situation, the trend of the flooding, and what's the people's perspective on this flooding. We generally we use machine learning and to identify these keywords, especially the address words, so we can feed that into Google API, Google Map API, and then at last we develop a product that can monitor in the nation where and when people are talking about the flooding. For example, we can zoom in into particular area and check what's going on there. And for example, people are talking about flood here. Or if there's a link, we can open the link and see what's the photos about. After doing that, we think we try to validate this method better, and we process the database with about 7 million tweets, and that's about the Hurricane Harvey in 2017. Generally, you can see that this is a big data. It has 43.2 gigabytes in terms of in size of the data. However, Twitter only has for privacy and for other reasons, people don't easily share the location. Only 7,000 tweets are geotagged, which means it has the accurate coordinates in their tweets. And especially after 2020, it's Twitter stopped people sharing. Even though you want to volunteer your accurate coordinates, you cannot do that now with Twitter. So with that data set, what we were doing was first we extract the Twitter data into two streams. One is the photos inside. The photos could be very informative. And on the other hand, we use the text set. If there's accurate, if there's the location names, we generally use the natural language processing to extract those names. And we define a local database, so we can compare the location name and database and try to guess what's the best location. Actually, people are not very creative to name their streets. For example, the First Street, Main Street, there's so many, so common in the United States. So if anyone mention those, I think our code is trying to guess what's the best location based on where the relative information in that message. And then we can convert that into coordinates, and then we combine with the photos into a data set that we can track what happened in the flooding event. For the photos, we generally classify into 4 categories. The first is impact. This is the first witness of the flood scenes that only available in social media. You can see that some photos are blurred, some photos quite in a difficult condition to read, but this is the best value of the social media that can complement into any public data source. And the second category is the preparedness. Generally, people talk about the weather forecasting or how people are preparing for the flooding. And the 2 last category about recovery and the response. So generally, there's the after flooding, people are rebuilding and cleaning streets. During flood, how people respond, for example, the reports in the field and how the rescue was conducting. So we classify these 4 categories, and we think that impact category is the most valuable category. And then we train a machine learning model that can tell what photos belongs to which categories. Generally, we captured the more than 4,000 photos about impact, and 700 about preparedness, and 1,000 about the response. The recovery is very low, which I think because of the database, it doesn't cover a very long period after the flooding. So generally, after doing this, we also validate with human labeling, and we get a very satisfactory results. So here are some interesting results we obtained. First of all, we think using the 4 categories, we can follow what's going on in the world. For example, we can track, this is how many people are tweeting about preparedness, and then this is how many people are tweeting about the impact of the flooding, and then recovery and the response. You can see that before the landfall of that hurricane, people actually talk very much about preparedness. But on the landfall day, people shift the focus to impact. And after 2 days of the impact, people start to talk about the recovery and the response. So we think that using this time series of the social focus, we can inform the rescue team and the flooding management teams what people are concerning about, what's the hot topic in the social media that maybe at this moment, we should still focus on preparedness. And after this, maybe this is the time that we should more focus on recovery and the response. And some other things we extracted is the distribution of what people are talking about this flooding. And generally, the red color are the impact categories that we evaluated the most. Those small red dots are only messages without any photos. So you can see over the city, this is Houston. On different day, you can see that people are talking about flooding at different locations. Well, it's one thing we observe here is maybe there's too much randomness and uncertainty, and we didn't find very useful patterns from the geospatial temporal distribution of this data. But still, you can see that how people are reporting over the time. On the other hand, we think still try to push ourselves, think what's the best use of such a big database. And later on, my student manually picked from the impact category and further classify the photos. We found 698 very high value images. These images actually covers wider spectrum of emergency issues. For example, trapped animals like horses, dogs, unusual animal presence in the city, such crocodiles, snakes, fire ants, and other damage of this infrastructure, for example, sewer, manholes, road damages that you don't usually see in public media, but the social media are very good to capture, to complete the big picture of the flooding events. And if you combine that with the very accurate address, for example, this is people say like highway, which road, which address, so you can see what's going on there. We call this as passive hotline. So people just tweet online, but we can forward that into the relevant agencies for help. With that, that's the first story. For second, during we processing this data, one flooding event happened, and then we quickly shift our research on this topic. This was a dam collapse in central Michigan that happened May 2020. So generally, very heavy rain happened on that day, and the east side of the dam collapsed. Governor declared a state of emergency and evacuated 10,000 local residents. And that was during COVID, so you can see the situation was really chaotic. This is the dam before collapsing, and this is during the collapsing. Local TV news station, they send a helicopter and go around this area and generally capture this footage. However, there's no monitoring system about this earth dam. Luckily, a local resident who used a cell phone captured a very good video that before and during the collapse. And we, through the public media, we contacted this resident, and he was really happy to share his video with us for analysis. So generally, you can see this is smartphone video. And to quantify the information or extract the information from the simple video, we use a technology called monoplotting. Generally, this is a method that you can map any pixel into the 3D DEM. So you know what's DEM, right? Digital elevation map model, which is the 3D map of the world in terms of elevation. So the general idea is that if you pick some key points on the DEM and also key points on the image, so you can correspond them together, and then at last you can determine where the camera was. So this is the place that we determine the camera position, and using DEM we can reconstruct the angle, the scene of the video. So from this we know that we can have a good overlapping of the two scenes together. One more thing we use is optical flow, which is used in self-driving technology. So generally it can follow objects over time. And we perform this analysis to follow where the soil coming from and how it collapses in the field. And the idea, if we know where the particle coming from and where it's going in time, we can 3D reconstruct that. So we make this a video. So to introduce what we found. And using this method, we can develop a 3D reconstruction of the event. We can also 3D reconstruct the field using the helicopter video and then make a measurement about the gaps. So for the interest of time, let me briefly introduce some other use of this technology. So we apply that into the social media. This is what happened. We try to find the flood extent, and generally from the video, we can from the photo we can see where it is. Using Google Street Map, we can map that into a field, and we can also, based on the submerge of like the cars tires and the trees, so we can roughly estimate the water depths in the area. We also do tests in the field. For example, we put a camera in a parking lot and try to look at what's the flooding area developing over time. But we have to overcome many difficulties. For example, there's a strong reflection from the water puddles, and there's the cars, there's a passing pedestrians. So how we deal with these things. But using some new technology, we can map this data into the video. So at last, we got the results over time, how the flooding pixels number changes, what the flooding extent changes over time. And we further tested in a remote place. For example, we tested in Puerto Rico. They have a very serious erosion problem. We put 2 cameras over the beach close to an airport. This is the cameras, and we captured the water boundary over time. And this camera also has night vision. We can, so the idea is how we extract the information. We use the new technology that Facebook published a new segmentation model. So this model is trained over 11 million photos with over 1 billion labels. So the good thing about this is given any photos, you just give a point, and then this model can tell you which this point belongs to. It can outline the boundary of this object. Using this technology, we can find the water boundary of the beach. So here is how the Meta's AI model, SAM, how it works in the field. So generally, it did a good job to identify the water land boundary. And again, we use this model plotting method. In this time, we can identify how the water level changes on the beach, and we compare with the local tidal gauge, and we got satisfactory results. But one issue with the camera is the camera usually has the cable is suffering from a corrosion problem, which is that's why the videos sometimes has to be stopped. So that's some other issues I just want to mention. I think before the end, for the interest of time, let's briefly introduce the last story. We also recently, as the large language model like ChatGPT and Lamar become available, we try to better use these models to do something with flooding risk communication. So we designed a chat app. So when the stakeholder or public, non-expert ask questions like a generate color-coded FEMA flood zone map for the area, New York City. So we provide this map and give relevant information. So what behind this chat app is actually we defined some functions. These functions can get flood map, can get flood data, can get the social vulnerability index, and also get a flash flood warnings. So generally these have complete functions, and because the ChatGPT can write code, so it can complete these codes to complete the function. And then we, using these functions, we call QGIS map. So either it's a flooding map or it's a flooding modeling results. We can inquire that using QGIS and return the values back to answer the questions. So here is some examples. Is there a flood risk for the proposed construction site at 777 Ben-Hur? This address, and it says this address is located within a flood zone as AE, and it's which indicates what the meaning of this AE. And generally, can you provide a detailed flood zone map for this area? And then it returns a flood map. Okay, so generally we evaluate the performance of this in terms of the accuracy, completeness, error handling, informative response, promptness, adaptability, and overall performance. We can evaluate the performance of that. So what we observe that for general inquiry questions like Wikipedia level questions like what's the flood return period, for example, those questions. ChatGPT is doing a very good job, but it's not very well in terms of error handling and information responses. Well, for flood warning, flash flood warning inquiries, because NOAA has a very good platform. Once we connected with that, ChatGPT usually is doing a good job to retrieve information there and answer users' question. Okay, so some take-home messages today. What we are doing in our lab, we show that AI can help extract unconventional data for flooding data collection, and this is I think will be helpful for practitioners to validate that numerical model. A new method is combining computer vision and AI is developed for coastal and urban flood monitoring. And also recently we use GPT to help support decision making, and it shows good potential for future use. Before I end, I think I would like to mention some other additional research directions. My lab probably not covering everything. The first direction is the machine learning based subgrid model. As you know that some model run very fast, but lack resolution to resolve like a parcel level flooding risk. How would you do with that? I think some researchers are developing model. You just run very coarse model, but machine learning learn from a refined model and then predict what's in the subgrid level. So in each cell, they can further define and provide information for higher accuracy in terms of address. And also machine learning is used to fill data gaps, and my lab is also actively working in this field. We recently published a paper how to fill in the data gap for satellite data, and also how to surrogate numerical model for optimization decision making, because you know that numerical model could run very slow. If you want to do optimization, you have to repeatedly run the code for many times. So sometimes it's infeasible. And how to using surrogate model, we don't need that comprehensive heavy model to run. We just run some machine learning model that mimicking the results of the heavy model. So in this way, you can run many times for optimization and decision making. Also for real-time forecasting, it's well, machine learning is relatively fast than numerical model. So generally, that's why real-time forecasting also probably need there's a good potential machine learning can be doing a good job there. So at the last, I would like to thank our team at Rutgers University and also our funding agencies. So here is the website of our lab and also my email address. Thank you very much. And please let me know if you have any questions.
Thanks, Dr. Wang. Very informative and a lot of useful information from this webinar. Definitely. Thanks for your time. I think we only got 5 minutes for questions, and I'm going through the chat. I think Nadia is asking what was a Google tool for the flood mapping in real time?
Yes, thank you for the question. We developed that model and tested for different scenarios, but currently it's offline. It's because you have to keep heavily maintain with the connection with the Twitter. Now Twitter charge quite a lot of money to use their data. So we currently stopped, but our code is there. If anyone there's a new requirement or new funding source, we are happy to explore if we can put it online again. Thank you.
Okay. Besides that, I haven't really seen any question, and I think several people asking about the survey, the link. So we put the link again in this chat. If you want to fill in, just click on that Google Doc directly. We're going to fix the QR code after the meeting.
Take one question in the Q&A.
Yes. Okay, see how we will incorporate the use of AI for NFIP community rating system in the next CRS manual or the revision of the entire program. Okay. I think that's a very big question. I'm not sure if Michelle, if you want to just off mute and ask by yourself.
It was more just a statement. This was
Okay.
fantastic. Yeah, thank you so much.
Yeah, sure.
Yeah, can I add to that? I think that's kind of one of the things that we can have further conversation on this at the conference or in the future kind of conversation. I hope that you will be part of that and we can kind of explore this together. So this is not a one-time webinar, right? We want to explore this kind of, path with members of ASFPM.
Yeah, definitely provide your thoughts or any in your daily job. I know the audience is broad here and people not only just dealing with technical work, maybe basically working on stakeholder engagement, everything. So if you have any use case you want to bring in for discussion, please feel free to reach out to us. Okay, so I think Jeff asking about the GitHub repository that you can post the code. I think that sounds like a question to Dr. Wang. If any of the code you developed for the work is open sourced, or you have any way you can collaborate?
Oh, we're happy to share the code, but it's not GitHub. We put some private repositories. So unfortunately, it's not available. But if you send email and we can see whether we have the some code to share, I'm happy to do that.
Okay. And there's another question about, has any of this data insights been published anywhere that we can reference? This is a fantastic work, and thanks for sharing. So I guess that's a question for Dr. Wang. Basically, any of the work being published available for them to cite?
Yes, we publish several papers on the social media work and also the dam collapsing. If you are interested, feel free to send me or check our website. We have all the paper listed there.
Okay. And there's a question about, could you or did you use local HH models to collaborate? Because many communities have them. So I guess that's about AI model results collaboration, like the comparison between AI model versus traditional HH model results. So I'm not sure if Dr. Wang, your work compared both approaches.
Just to clarify, HH model is the HAC HMS.
It's hydrology and hydraulics modeling. So HAC HMS or HAC RES are two typical software people are going to use. Yeah. Yeah.
I think ourselves is running those models. So we do coastal flooding, we do fluvia flooding. Currently, we don't surrogate. No, I think we developed some surrogating model for the coastal flooding models, and those relatively works well. I think another thing we are trying to do now is try to use ChatGPT to explain questions and maybe run new models. So that's something else we are trying to do.
Okay.
Yeah, thank you.
Okay, what version of ChatGPT was used? I think that's a question on the third.
Yeah, so we use the GPT-4. It's actually we use the API of the OpenAI.
Okay. Next one, do you have a repository of prompts that are used for stormwater management / floodplain management?
I think my student, we recently wrote the Hacker. Yes, so for the GPT one, we have those information in the paper. We actually put an archive paper now online, and my student has a repository, GitHub repository. So if you want to check what prompts we used here, feel free to go there. If you cannot find it, please feel free to email me.
Okay, I think that's the last one. I just type Dr. Wang's lab address directly in the chat, so people are a little bit easier to click. Can you, Dr. Wang, do you want to put your email directly into the chat so people may be easy to contact you? And someone was asking the slide deck. We're gonna share the slide deck after the webinar. to everyone. So, okay, so if no more question, we're 3 minutes over the meeting, and one quick announcement I want to make is in the upcoming 2024 ASFPM conference in Salt Lake City, we are going to host a in-person kickoff meeting of this subcommittee, which is currently scheduled on Monday, 1:30 p.m. to 3:30 p.m., the second half of the Higher Education Committee meeting. So the place haven't been, like the conference room haven't been determined yet, but more details will be uploaded to the app when the time closes. So if you're interested to meet us in person, please come to the event and we can talk more on this topic. All right, with that, I'm gonna end today's webinar, and thanks again for Dr. Wang's time and his insights and great work about AI applications to flood risk analysis to the whole community. So thanks for everyone's attending, and hope to see you next time.
Thank you. It's my pleasure. Thank you very much.
Bye.
Thank you, everyone. Thank you, Dr. Wang.
Bye.
Hey, thanks, everyone.
Thanks.